Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. This week, Guillermo and I explore the aims of the CryptoPunk movement with co-creators Alex and Nicola. Alex is a long-standing builder in the crypto industry, most recently as a co-founder of Flashbots, and is now the program director of ARIA, the UK's DARPA equivalent, where he's currently focused on funding new cryptography based on natural laws. Nicola has been leading the cryptography R&D effort at Protocol Labs for the last 8 years and also founded the syndicate Deep Crypto. In this episode, we discuss the Quantum Punks Manifesto, returning to the topic of quantum cryptography and looking at how this compares to other eras in more familiar cryptographic areas. It was very exciting to dig back into the quantum cryptography side of things. We get a chance to cover lots of applications for this stuff. So yeah, hope you enjoy. We do reference an event that Nicola and Alex held in Paris back in March. We're going to try to dig up the links to these videos. We mentioned them a couple times throughout the episode, so look for these in the show notes. Now, before we kick off, I just want to let you know that ZK Summit 13 is happening on May 12th in Toronto. The event is coming up fast, and if you haven't yet bought your ticket, we do encourage you to do so. Also, we do have some student tickets still available, so if you would like to apply for a student discount, you can do so over on our website, zksummit.com. Hope to see you there. Now, Tanya will share a little bit about this week's sponsor.
You might already know the ZK Jobs Board, a place where teams can share open roles with our community. But when it comes to key hires, finding the right fit in our niche space can be difficult. That's where Missing Link comes in. They're a talent team built for the Web3 era, helping projects across the ecosystem connect with the right candidates at the right time. They've worked with names you'll recognize: Ethereum Foundation, Matter Labs, Lido, Mina, Web3 Foundation, and many more, filling critical roles that drive these teams forward. Whether you're an established project looking to fill a senior leadership role or a startup searching for specialized talent to refine your product market fit, Missing Link can help. They've done it for some of the biggest teams in the space, helping them, and now you, find the right people fast. For more details, check out the show notes and visit their website at missing-link.io. So thanks again, Missing Link. And now, here's our episode.
Today, Guillermo and I are here with Nicola and Alex, the co-authors of the Quantum Punks Manifesto. The quantum punk community explores the intersection between quantum and cryptography, and this is hopefully what we're going to get a chance to jump into today. So welcome to the show, Alex and Nicola.
Thank you for having us. Happy to be here.
Thank you, everyone. Happy to be here.
Hi, Guillermo.
What's up?
Excited for another quantum episode?
Yeah, I know. It's great. I get dragged onto the physics stuff, which is harking back to old memories.
Yeah. So just a few weeks ago, Guillermo and I did an episode with Jelena Vukovic where we did an intro to quantum engineering. I'll add the link to this in the show notes in case the listener would like to get some background. Today, I feel like the focus will be primarily on the overlap between what we covered in that episode and the cryptography space. We're going to be talking a little bit more about that intersection. When I think about quantum and cryptography, I feel like it might be good to just kind of define a few different ways that we hear those terms combined. One is like quantum will break cryptography. So some classic cryptography they don't think will stand up to quantum computers. There's also post-quantum cryptography, which is current cryptography, classic, which people think will be able to stand up to quantum computers, won't be broken. But then there's this third category, which is quantum cryptography. And I feel like when it comes to the quantum punks, this is the area you guys are most focused on. Am I right?
Absolutely.
Cool. Okay, but before we do jump in to this quantum cryptography built for a quantum environment, I feel like it would be great to talk about your backgrounds and what led you to work on this. I feel like I know both of you originally from the ZK space, actually, or I've seen you at events, you were both involved. Nicola, let's start with you. You were actually on the show long ago. We did an episode. I recorded it at ZCon 0. It was like an event episode where I interviewed about 13 people, and you were one of those interviews. At the time, you were focused entirely on ZK. So what's been your history since that point? What got you into quantum?
So what happened is back then it was I would say the first few years of zero knowledge proofs.
Yes.
And I was working at Protocol Labs, and I worked at Protocol Labs for over 8 years. And I led the cryptography and protocol design R&D team. There we worked on making zero knowledge proofs more and more practical. And in a way, back in those days, like a few years before, I was a PhD student at MIT, and some of my professors told me, well, ZK is still academic material.
Not going to work.
And it's insane what happened 10 years later.
Yeah.
And in a way, when looking for what is today at that stage, we looked into quantum cryptography. And to some extent, when we talk to professors about quantum cryptography, these professors tell us, well, this is academic material. And in a way, I relived that experience. And in a way, Alex and I built thick skin on people not believing in super early technologies. And so I'm very excited, actually, when I hear that in quantum cryptography.
And did that get you started? That kind of got you excited and you decided, okay, this is what I want to work on now?
This is more like an exploratory area for me. I love this working on this moment of a technology where it's unclear if it can be practical, but the more you dive deep into, maybe there is some low-hanging fruits.
Nice.
And I'm actually very excited to find either myself or to help other people find. That's why we wrote the manifesto, to find more and more intersections between quantum and the cryptocurrency industry and quantum, so that we could have new applications and maybe better hardware driven by these new applications.
Nice. Alex, what about you? What's your background and what led you to work on this?
Yeah, so I've been more around the cryptography sector. So before the quantum punk stuff, I was building flashbots for a few years. There's some privacy element to what we were doing. We came at it from this very practical perspective of, okay, we need to add privacy to what we're doing. And we went more in the trusted hardware direction, but we still explored all these other primitives. And before that, I was running these ZK meetups in London and having fun doing that in like 2017, 2018. And so, yeah, I've been around and super interested in cryptography, always thinking that cryptography is one of those things in the blockchain industry that it feels very tangible to me. And so whenever I have like a crisis of faith, cryptography is one of the kind of like stable point that I kind of go back to, and I'm like, this has applications way beyond the industry that I'm in, and it's also just so fascinating, and it relies on something that I can understand, which is like, okay, it's based on new maths or new methods that are kind of like understandable. And so Nico and I were meeting regularly to catch up and hang out, share ideas. And he kind of told me, dude, like quantum is booming. It's super exciting. And I'm hearing about this quantum cryptography stuff, but it feels a little bit like far. Maybe is it too far? And should I focus on IO or should I focus on this instead? Like what are the problems that I should really focus my next, big adventure on? And when he told me about quantum, I was like, dude, this is sick. This sounds like the most exciting thing. And also, even if you think it might be a little bit further away now, you're not factoring in our own power to potentially accelerate it, the same way what we've seen with the zero knowledge space. And so we kind of committed to, okay, let's explore it. And from there, we kind of started going to events, looking really stupid and asking like very basic questions.
Like quantum events? Or
Yeah.
Okay.
Exactly. We went to one particular quantum event where it was full of quantum companies. And we just showed up, we're like two little like, hey, we're from the crypto industry. And so, people were like confused what we were doing here.
Nice.
And we were just asking basic questions. And I think from that event specifically, we came out of it both realizing, okay, there's a gap here. They don't know that there's a whole ecosystem that is so hungry for new cryptographic primitives. And that if you give them those tools, they're like, get so excited about the types of applications they can build. On the other side, the crypto people don't seem to be aware that this exists. And when you mention quantum, it's usually about post-quantum secure systems. And so we just felt, okay, there's an intersection here, not only a gap in communication, but also a gap in culture, where the event we went to felt a little bit like corporates and trad. And we were like, where are the hackers? Where are the like misfits, We're the people that are kind of like overselling their projects, which is like super common in crypto. And you kind of need, to some extent, you need the dreamers, you need the people that are like really thinking about the big picture.
I was just thinking like the brainstormers or the idea people. It sounds like the ones with the weirder ideas. Yeah.
Exactly. Missing the idea guys, missing the philosopher kings, whatever you want to call them.
Thought leaders.
And so from there, we were back in the taxi at the end of the day. And we were like, dude, we have to do something. We have to at least point out that this intersection exists. And from there, we worked on, okay, let's write a manifesto. That's like the most, culturally appropriate way for us to do this, so that we really bring the values we think are important to bring in there. And so that's kind of how we went about.
Cool.
The manifesto is actually, it's actually quite lovely. I mean, it's a short document. It clearly outlines stuff. I came in, for what it's worth, very skeptical because, as usual, sorry, Alex, I actually know you quite well, so I was less skeptical because of that. But nevertheless, I was somewhat skeptical, and was like, oh yeah, like quantum. The number of times I've heard quantum in like the years before I studied it, and then when I studied it, and then afterwards has been hilarious. But then I read the thing and I was like, no, actually, this is quite reasonable. I mean, obviously, still forward looking for sure. But it's an easy thing to rally around. It's clean, it's clear. I was very impressed in the writing. Like, honestly, I say that about very few quote unquote manifestos, but like this one's actually quite good. So yeah, very excited to dig into the philosophy, ideas, notions, constructions behind all of this stuff.
Thank you for all the compliments. I'm glad you say that.
I'm glad you say that because we actually spent an insane amount of time on this manifesto.
I can tell, yeah.
We wrote it in 10 different versions. And then I remember one day I said, Alex, I think maybe we need to write it from scratch. And and that happened several times. And but I think Alex has been a meticulous author and editor of a lot of this.
Yeah, no, I mean, I feel that deeply because that's a lot of my papers often go through complete from scratch 4 or 5 rewrites, and I can tell that happened here because the ideas are very clean, they're nicely organized, they say exactly the thing, 2 sentences to describe it, no more, no less. And I'll stop with the effusive praise, but nevertheless, this is very cool.
Maybe we should actually jump into what's in this manifesto. Do you guys want to share with us sort of the overarching ideas, what you're trying to cover?
Let me just give you some context. Like Alex said, there is a big gap between the two communities. And we wanted to find some applications that would make both communities excited. And in some ways, quantum cryptography, it's not something new. People have been studying theoretical applications of quantum cryptography. And not only, for 10 years plus, there are companies that build quantum key distribution systems. But a lot of these systems have applications mostly in defense. And in a way, it's like for secure communications between armies or banks, I don't know. But it's very cybersecurity oriented. And if you think about the early stage of the internet was some sort of defense communication technology.
Totally.
And so we kind of wanted to try our best to wake up people and say, hey, if the internet stayed at defense, we would not have social media, e-commerce, TikTok, and similar things.
Yeah, I don't know if we want any of those things.
True.
But yeah.
True.
But, I mean, the
you mean like the world we know today would be different?
Let's say that. But, and what happened in cryptography? In a way, even cryptography started as defense, and then we started thinking about what can we do for the final users. And so what tool can we build so that the individual can feel more powerful? And so this was what started the cypherpunk movement back in the 80s. And so Alex and I spent some time thinking, what if we could bring some cypherpunk to the quantum industry? And the more we looked into this, the more we realized that quantum cryptography is some sort of a cypherpunk endgame, where there are things that you can do with quantum cryptography that you cannot do with classical cryptography. And so not only we could use quantum cryptography to better secure existing systems from quantum computers, but we have a way to build new cryptography. And we're going to touch on that into the rest of the podcast. And new cryptography primitives have generated an incredible amount of value. In a way, encryption gave us private messaging, signatures gave us HTTPS and the ability to do e-commerce online or communicate online. And consensus gave us blockchains. We're yet to see what zero knowledge proofs are going to give to the mainstream users. But I wonder, what can quantum cryptography give us that we cannot think about, because you cannot just do it with classical cryptography. So that's how it started. And there are two main theses in this manifesto, which is quantum accelerationism, and the other one is new applications of quantum cryptography for cypherpunk applications.
Cool.
The cypherpunk applications, it's kind of repeating a little bit of what we said before, which is saying, hey, if we have new cryptographic primitives, by new, I mean they enable new capabilities. There are new applications we can build with it. And the kind of product market fit for these new tools is probably cypherpunk applications, just because in the cypherpunk ideals, we care about the most secure systems, and we care about some of these guarantees a lot. Trustlessness or trust minimization is critical. For some other applications, it isn't. And so on one side, it's to tell people from the privacy and cryptography industries, you guys should look over here. This is probably the end game for what you want to do. These are the systems that will be the most secure. These are the systems that you might even...
They're secured by physics.
Exactly. Secured by physics instead of computational assumptions. You might not even need to rely on hardware anymore, thanks to some of the new primitives you have.
Wow.
And you have these kind of new world of primitives that emerge. And so the first one is new applications can be created with this. And the second kind of tenet of the manifesto is those new applications are going to garner funding and demand from users, but also funding from investors like Guillermo on this call. And that creates a virtual cycle that we've seen. And we're very familiar with it, which is the space accelerates, researchers start working in industry, whole teams start being pushed from academia to startups to accelerate specific primitives on a specific metric that is incremental and so less interesting to academia, but very interesting to industry. And from there, what you get is an acceleration of quantum hardware more generally. And so the quantum acceleration is that by having more demand for these primitives, you have more demand for the underlying infrastructure that enables them, which creates this broader movement within quantum technologies, not only quantum cryptography. And that has this kind of knock-on effects that can bring about the general kind of benefits of quantum technologies that go beyond just quantum cryptography. And so it is kind of saying a new growth vector that can come into the quantum technology space that is not the quantum computing paradigm or narrative, nor is it the quantum sensing narrative, but the cypherpunk applications of quantum networks. And so the first point, new applications, is us talking to cryptography people. The second point is us talking to the quantum people. So telling the crypto people, there's cool applications here for you to build. Telling the quantum people, there's demand that you're not looking at that is coming. That's the kind of duality of those two statements.
When you were meeting with the quantum folks and you were going to those events, you sort of mentioned it's a little bit corporate. I've only been to your event, which was meant as like a kind of mix of the cryptography people and the quantum people. But what sort of struck me with the quantum side of things was I got the sense that they're a little bit more like Web 2 classical startups too. Like even if they're small, they're still like they're hardware. I mean, I don't blame them. It's sort of they're dealing kind of with these hard primitives, expensive timelines. They're going to have to think very long term in order to raise money, and it's just like a very different business. Do you imagine sort of new startups coming out in the middle in that intersection, having a different spirit? Like, aren't they still going to be constrained by the same issues of like timelines and expense the minute they start playing in quantum?
I mean, first, there's already these startups that have started emerging. Some people that helped co-write the manifesto and kind of reviewed it were like people that are now started companies in that space, raise money from crypto investors, and some other are rising in that space. So it's already happening. And what we found and what got us excited is that when we posted the manifesto, it resonated with quantum people. And they said, I cannot believe that this was written because this is the energy we need in the space. A lot of these quantum communication people were like hackers in their past, or came into quantum communication because it was, the most secure systems, So a lot of them have that mentality. And the only reason they're not really embracing it is because where's the demand? We can build these kind of systems, but we don't know that there are new applications beyond the current ones. And the current ones are this kind of defense-related applications or kind of very primitive applications that is quantum key distribution. Or you have to kind of enter the fold of quantum computing and you have to serve their needs because this is where a lot of the narrative is, both funding-wise and also just hype-wise. And so in a way, we're kind of saying, let us create a new narrative. And some of these people are ready to jump ship and like to kind of like slightly steer the direction of their company towards where they really believe in. And this has been recurring. It is not like universal at all, but there's definitely a set of people that believe that. That being said, you're right that there is this hardware component to quantum cryptography.
That's what I was going to say. Also, you just mentioned quantum communication.
Yes.
And then there's quantum like there's quantum computing. There's sort of like these different components that we learned on the last episode. Like, are there some parts of the quantum space that are more flexible and faster? Are they all sort of stuck in the hardware side of things?
No, I mean, so quantum communication is like, let's say the supersets, and then quantum cryptography is just secure communication in a way.
Okay.
But you're using the rails, the quantum communication rails. Quantum computing is more, you could consider it like local communication in a way, where you don't need to necessarily share a quantum state to another like quantum processing unit. And then you have quantum sensing as like the third broad category. Quantum sensors, my understanding is some of them are quite mature and used in some applications already. Quantum computings are the ones that have garnered the most hype, but haven't really delivered on like useful applications yet. And so they're in that state, you know, somewhat blockchain-y state of like, you know, selling a lot of promises, and people are excited about them. And the quantum communication side, you have some primitive applications, and what quantum communication requires, from what we've seen, is very little kind of hardware for it to work for some applications.
Okay.
And so part of the manifesto is kind of saying, hey, instead of focusing on quantum computing and on kind of basing your timeline a little bit the way Guillermo discussed at the beginning, like being a skeptic because computing is far away, quantum communication you can use today. You can use an optical fiber to share a photon that you've encoded information in between two parties, and you have these networks that already exist, spread kind of all around the world. They aren't huge, and there's still a lot of work to do, but this is kind of a technology that we can start using at a primitive level. That being said, there's still this hardware component, and so. Relative to starting a cryptography company, let's say, where you can really
still hard.
Yeah. I mean, you have to either build your hardware or you have to use someone else's hardware, and it is not deeply expensive, to be honest with you. Like, you can build a very basic quantum network on your table, you know, like a few nodes or something like this. I don't know, Nico, if you have a price range, but you're like maybe 500K or like 600K.
Oh, not much.
I'm surprised it's even that expensive, just using like a photonic setup. But
the most expensive part is the photon detector, and then it depends on the application you're trying to do with it.
Right.
The more kind of features you want your network to have, the more expensive it can get. If you want the leanest, definitely cheaper than like 600K.
You could make a nice like tabletop for under 10K, I think. But like just it would be a demonstration of a cool thing, not like a useful necessarily.
Yes, or also depending on if you buy off the shelf or if you buy like parts that you then build yourself, that's a big component. You have hardware providers that you can buy off the shelf from, but there's a huge markup on that, obviously.
Yeah.
If you're savvy enough to build it yourself, then you can get the cost down to maybe 50K or 60K, you know, but all of this to say, there's a hardware component, you have to wrestle with it, and that makes it kind of cross-disciplinary to some extent, a little bit more than cryptography, because you need that kind of somewhat hardware expertise, or at least an intuition and understanding of what's going on in that space, and then also the understanding of protocols and cryptography.
I just want to add one thing, which is if you're scrappy enough, like a small startup, I think there is a big secondary market of these devices that are not used by the startups that are pivoting away from this. But I just want to say one thing, which is one of the intuition that Alex and I had was that in quantum computing, we have to wait for better hardware. And the question is, do we need to wait in quantum cryptography for better hardware, or can we use existing technology? And it turns out that there are applications for which you can just use existing technology. There is no new open question. It's just like Alex said, put pieces together, or like have professional systems or professional network operators that put these systems in a cloud-like facility. If you want to run like some nodes in a network to run some protocol on a quantum network, you cannot really do this today. which is crazy. Like we're coming from a Web 2, Web 3 experience where you can just deploy a smart contract, or you can just open an AWS account and you have the cloud going. For quantum communication, you cannot just do that. I think we are very close to get to that point, but we don't have easy to access quantum networks. If you want to deploy an application, most times you get told either to engage in a contract with some of these network operators or to talk to a university to give you some nodes. Like imagine saying this to a builder in the Web3 community. And so this is like the role in a way of the quantum punks movement to say, hey guys, there is a whole community that can grow out of fiddling with things or hacking on things, on open source software. And there are players in the space that are thinking the same way as us. And this is very exciting. And so hopefully we do our little to change that mindset.
I want to dig into two things. One of them would be like more specifics around what this thing is, like what this would enable. But number two, I want to point out something kind of funny, right? Which is the anthropology here. Like, I mean, the culture of like physics and physicists from like PhD labs who know this stuff is in some sense completely different than the anthropology of like the, 10-year-old programmer who grew up to like want to do cryptography things, right? I don't mean that in like a deterministic sense. I don't mean in like it's always the case. It is just kind of funny, right? Like you go work at a physics lab, you have all this very fancy equipment that's like, millions upon millions of dollars. There's like a certain scrappiness that comes from that. But there's also a certain thing about like, oh, we have to do, things the way that they were intended to be done by like the previous, generation of physicists who entered this lab. And it's kind of interesting. I mean, it's not everyone's like this, of course. And there's like weird pirates out there who like just go and build shit for fun. But anyways, it's kind of interesting because like it's kind of like a slight cultural distinction of the two. I think the other thing that I want to point out, which I when you say it, it sounds so kind of trite, but it's like very neat, is we now have the technology, even if it's not 100% perfect, but we can build real things. Is like, again, like a weird ethos thing, right? Like a lot of people who come into this field, it's like a very particular field. Like cryptography was a thing that you wouldn't teach undergrads up until pretty recently, because it was really written in papers. It wasn't really written in like a standard way, right? You got to go do a PhD on this thing. Like physics is kind of still that way, right? Like doing real like deep quantum stuff like kind of requires you chew through a bunch of papers and stuff.
Like you have to be further along in your academic career to get there.
Yeah, it's like hasn't been systematized enough to make it legible for people who don't want to stick out this like long journey. So it like almost self-selects for this interesting like person who is kind of willing to chew glass for a long time before they're able to kind of get to the top, right? But as it gets systematized, because technology gets better, people get better at explaining these things, we have better abstractions for the thing, right? Now this intermediate layer of like kind of crazy pirates who just like come into the field. Yeah, exactly. Want to just build things, or like, I see where this is going and we can start building it. Just like becomes like, in other words, the field becomes legible to like this like higher level like people who are just like willing to like start startups around this stuff. Just like comes in. And I think, I mean, obviously this doesn't happen in a vacuum, right? Like you guys are part of this in like writing this manifesto, right? Like you're making the field legible to people who are not simply like, 7th year PhD students working on a transducer or something.
Mm-hmm.
I kind of agree. Like, not only, I think that quantum cryptography, just to give you context, it is a very small niche field.
Yes.
At QCrypt, there is, which is the main quantum cryptography conference, I think there are 300 attendees. If you do like maybe a rough estimation of like 1 to 5 professor to student ratio, maybe this ratio is wrong, I don't know. But what I'm telling you is that you cannot have more than 300 experts in quantum cryptography. And some of these people are not even computer scientists, they are physics people. They are trying to earn, in QCrypt no, but there is a broader community of experimentalists. They are trying to build these systems in practice. And so not only is it very hard to work on these things, but the combination of these two fields is an insanely small niche.
Yes.
And so the drive that you need to have in order to be working in this intersection, it's very strong. But in a way, it reminds me what happened in the early days of cryptocurrencies. You had people that you needed to be an expert in a way, in cryptography. Like in order to understand cryptocurrencies, you needed to understand consensus and what it meant, or in order to work on zero knowledge proofs, you needed to have like a body of knowledge that was there was not a short summary of what these things were, or like an easy explanation.
There's no ZK podcast.
Yeah, there was not
Exactly.
ZK.
Well, actually, when
Podcast.
ZK Podcast started, I think it was still like that. But yeah.
But, I mean, I think Anna, but you contributed to making it more legible.
This is exactly it. Yeah, Anna, like you are making this legible,
100%.
In the early days of cryptography, you needed to have a strong understanding of cryptography, a strong understanding of economics, and then a lot of imagination. And so this is the point in which we are right now. The field is not empty. There's a lot of theoretical quantum cryptography, which is very exciting. And there is the beginning of applied quantum cryptography. We have QKD. We have it for like more than a decade now.
What's it called? Web? What did you say?
Oh, QKD.
QKD, quantum key distribution, is let's say the only practical and piece of technology of quantum cryptography that is sold today
Okay.
to final users.
Cool.
It's about we can talk about it in a second, but the thing is there is just that, and we need more creativity and more intersection between these two fields.
I want to dig in a little bit more into kind of the previous thing we were talking about, which is, okay, let's say we have, the AWS of like quantum communication over short ranges or something, whatever. I mean, feel free to place whatever constraints you want on it. And you could launch, there's some nice abstraction for what this means and all this stuff, which are questions that are outstanding. But what can we do with that? Like, you could launch like a service that like does this thing for you. Like what are some things that might be enabled? Like that might be interesting that people haven't done yet, or maybe that people are doing, but like on a lab setup as opposed to doing it, out in the wild with some like cool code that like executes a thing out there.
Let me start with maybe with the North Star.
Okay.
And then we can go back into like what you can do. And this is also helpful to give an intuition of what we're talking about.
Mm-hmm.
And most importantly, it's a way for me to spread a meme, which I think is very strong, and it's quantum money. And most people in physics or in cryptography, unless you work on quantum cryptography, you're not aware of what it is. And I find it quite surreal. So in the 60s, there is Wisner, the first quantum cryptography researchers, that writes a paper that sits on a shelf for 15 years, rejection after rejection, 15 years plus actually. And then at some point in the 80s, this paper gets published and it's called Conjugate Coding. And in this paper, he talks about like two main examples of like ideas that you could do with this. And one is quantum money. And we're talking about like 25 years before Satoshi Nakamoto wrote the Bitcoin paper. So this quantum money this idea of quantum money, which I will describe in a second, predates even the cypherpunk movement. So it's incredible that a person had this paper on some shelf that talked about peer-to-peer money and at the same time started a field of quantum cryptography. So let's talk about quantum money. Before we talk about quantum money, let's talk about physical money. In a way, gold coins. I have a gold coin, it's in my pocket. I give it to you, Guillermo. In that moment, you know it's in your pocket. The transaction is instantaneous, it's private, there is no third party that needs to be notified. What a great piece of technology.
Mm-hmm.
The only issue is that you cannot send it over the internet. And so we need to meet in person. And this physical annoying thing. What we want digital-like communication. So that's why we went from physical money to digital money. Digital money is like a file. You encode money in a file that I send to you, but at the same time, I could send to Anna, and that's a problem.
Yeah.
So we need to make sure that there is someone else, a third party, let's call it a bank, that orders these transactions.
Or a
And
ledger.
so all in a sudden, exactly. Or you can take the bank and distribute the governance on many people with proof of work, and that's a blockchain. So even blockchains don't remove the bank; they just
No.
replace the governance of the bank. And this is the problem of digital money, because I can send the same file to two people.
Yeah.
Double spending, essentially. And so the question is, can we build money that can be transferred in a digital-like form that have physical-like properties? Meaning, that once I send it to you, they leave my pocket, they enter your pocket, the transaction is settled, and no one needs to witness it.
And it could never be cloned or copied.
Correct.
Yes, absolutely. So, and quantum money uses properties of physics, like the no cloning theorem in particular, which essentially says quantum information cannot be cloned once you receive it. And so you cannot try to look into the information, say, stored in the quantum state, like preserved in the quantum state, because the moment you try to look into, you disturb the system and then you lose information. And so if I could encode money in a photon and I could send it to you, it's like from my pocket to your pocket, then I cannot send this money to send these photons to someone else. The issue is where are you going to store these photons? We don't have USB sticks for photons yet.
Wow.
And so that's why I said before, this directionally is the North Star. It's one of the applications that we can look into as North Star. And it for sure is an application that a lot of Web3 people can resonate on. In a way, is a very cypherpunk application.
Totally. This, by the way, like in our episode with Yelena, we did cover teleportation and the no cloning theorem. And I'm guessing that's what you're discussing here. This, like, is that teleportation in a way? Because it disappears on one side and appears on another?
No, it would just be no cloning. The teleportation part happens in repeaters. So because this no cloning thing, most people would tell you that it's annoying, because they will tell you that in normal networks, you repeat a signal over so that you're able to amplify the information that you're sending, because you can copy it. And so that allows you to send information far, far away. In this case, if you're trying to amplify this photon, you would have to copy it, and you're not able to do this. So you have to build a different type of amplifier and different type of repeater. This repeater is based on, it's entanglement swapping based. And so you use this teleportation property.
Oh, okay.
Kind of like transitive maths, if that makes sense. Like A to B, B to C. So you can do A to C, or like the B part, you do this teleportation thing, which is, teleportation is just a cool name for it.
It is a pretty sick name, actually.
It's an awesome name.
It's a good advertising department name, like
100%.
Quantum teleportation.
The way to think about it is that there are two different layers of the stack. One is teleportation is useful for the networking stack. In a way, if I have the photons that I want to send to you, I can send them to you directly, or I can use alternative technologies to send this quantum state to you, like quantum teleportation.
I see. Yeah, it's the in-between. So does it really have to do with how far away you are, like the distance?
Yes, exactly. Again, let us preface some of this with the fact that you should see us as crypto people that are entering the quantum space for the last year and that are like learning. So we are maybe further ahead than some of the listeners, but we are still learning. So my understanding is that the photon gets absorbed in the optical fiber at about 100 kilometer. It gets absorbed before even, but 100 kilometer is kind of the distance of. After that, you need some form of repeater. You have trusted repeaters that actually decode the information, read it, and then reissue a new photon. But then at that point, it's trusted. So you kind of lose a lot of the cool properties. Or you have these trustless repeaters that are based on entanglement swapping.
Teleportation.
And then it's teleportation.
Got it.
And so the trusted repeaters is what a lot of QKD networks today are using. And the trustless repeaters, some of them are built, but they're quite primitive. And there's a few things that they need to improve. One of those things is what Nico mentioned before, like storing the photon for a little bit longer. So slightly better quantum memories helps this like repeating process to happen. Or if it fails, you can do it multiple times because you're still storing the photon, basically.
I have two, so maybe slightly lower level questions, and it's okay. Feel free to not answer them if you're like, this is too stupid. The first question I have around it is, surely we can use the no cloning theorem, right? Like we have something in some state, right? And I just give that to you, right? And via no cloning, we can certify that I cannot clone that. I can't just have that in my pocket and give it to you. The problem is like we need to still verify the thing you've given me is money, right? As opposed to just being like some arbitrary, like made up, new state, right? And to do that, we have to measure it. So how do you ensure, like when you measure, this piece of blob that hopefully is money, but you do not know if it's money, right? You destroy part of it, right? This is like the same reason why no cloning is a thing. So how do you ensure that like the blob I've given you, which could be, hopefully is a coin in my pocket, but actually could be some made up nonsense that like vaguely looks like a coin in my pocket. How do you ensure that's a real token?
As a computer scientist, the formal answer that I would give you is that there are protocols that define this property as a local verifiability, which means that there are some quantum money protocols that you can locally verify, meaning that I don't know the physics part of it. I don't even know if we have constructions for it, but technically people have been thinking about this problem. I'm a slightly more expert in, say, private quantum money. So quantum money, we cannot have them today, mostly because we don't have memory. So
Sure, yeah.
thinking too much about quantum money, it's a bit of a problem. It's something that I really want, but I cannot have until we have innovation in quantum memory.
Right.
And so, but what we could have in the short term is a private quantum money. And private quantum money, it's not something that Web3 people will be insanely excited about. But the idea is that as long as you have, I call it a minter, but you can think of it as a bank or like a node that is the trusted node, the mint token. What you can do is you can ask the minter to mint tokens on request, and you can engage with the minter in a protocol to verify that what you have received are quantum tokens. But this requires interaction with the bank. So I'm not aware of any protocol that gives local verifiability in private quantum money. But there is a way to do that. What I'm saying is, worst case, as a super applied pragmatic person, I tell you, well, worst case, you just talk to the bank, and the bank will engage in the protocol with you in an interactive protocol. They will verify the tokens.
Maybe Nico, it's worth instead of looking at quantum money, explaining how like a quantum key distribution works, because like I think the question of Guillermo is like the more basic, like, hey, this information that I've encoded in the photon, sure, it's temper resistant. If anyone intercepts it, they can't read it, but the ultimate receiver of that information, how can they then read that information?
Yeah, of course. So again, like Alex said, let me put a big disclaimer here, which is I'm a computer scientist and I don't come from quantum cryptography, but I'm here to learn and be corrected. I also gave a presentation in the past where a professor told me, well, this triangle they drew is incorrect. And I was very happy about that. So if you're listening and I say something wrong, please reach out. I want to become a better quantum cryptographer. So the idea is the following. QKD is the problem of quantum key distribution. So before cryptography, you and I want to encrypt a message so that other people around us, like an eavesdropper called Eve, cannot listen to our message. So before, let's say, modern cryptography, the way we did it in an information theoretically secure way, it was that we come up with a long pad of numbers, 01010101, that we used to shift the bits of our message. But when we come up with this one-time pad, we need to meet in person to exchange it, because there is no way to exchange this one-time pad in a secure way. So this like let's say Claude Shannon cryptography. And then Diffie-Hellman showed up and they said, well, there is a way to do key exchange, but you need to add assumptions. You need to assume that some problems are hard for computers. But the issue is that these protocols are not resistant to quantum attacks.
Because the quantum computers can
break the discrete log.
This hardness.
Yes,
like,
exactly.
It's hard to find the solution. It's hard to, like, you need endless hours of computation in order to solve this problem. And now all of a sudden a computer comes along where it can do it faster.
Yes. So the crypto, I like to introduce like a new meme that I like a lot, crypto mathematics and crypto physics. because the word quantum means so many things. If I say quantum cryptography, a lot of people will misunderstand it with post-quantum or quantum cryptography. So
Yeah.
let me just like simplify it for everyone. There is mathematics, there is crypto, there's cryptography that is based on mathematics. Or what I mean by this is a simplification. It's based on assumption of some hardness of mathematical problems. And that's the cryptography that we used. And some of it is post-quantum, some of it is not. And the one that is post-quantum, like, we don't really know.
We think it's post-quantum.
Yes, exactly.
Post-quantum until it's broken.
Yep.
Yeah. And it could be that we don't even have to wait for quantum computers to break some of this post-quantum security. We've seen it with isogenies in the past few years, and we saw with some like assumptions in lattices and so on. But anyway, so going back, there is a crypto-mathematics, which has mathematics as assumption, and then there is cryptophysics, that has physics as assumption. And so we have this one-time pad, but we have to meet in person. Okay, then there's a modern cryptography, Diffie-Hellman, but it's broken with quantum computers. So the question is, can we build a way to exchange a secret key, so that we can later encrypt our messages that does not rely on mathematical assumptions and instead relies on the laws of physics? Okay, this is the hypey way to say this, but and the way it works is like this. So there are two parties, each of them sample quantum state. And I'm going to explain, for those that want to look it up later on, the BB84 protocol. And it's like a milestone paper that is a subsequent paper on the conjugate coding paper from Wisner. And so in BB84, you encode information in a quantum state, which could be in the form of photons. And both Alice and Bob sample these BB84 states, and then they send them to each other. And then after they receive each other's state, they measure it. But the beautiful thing about these BB84 states is that they can be measured in two bases. So Alice encodes them in a specific basis, and Bob measure it in a basis that is random. So sometimes it's the same. If it's the same, they're able to extract the information that Alice sent them. But if they don't use the same basis, they will get random information. That's the property of quantum. And so they engage in this protocol, and then they talk with each other in a public classical channel, and they say which indices of these BB84 states they read in the same basis. And then there is like some other protocols to figure out like if Eves was in the middle. And so this is an example where you can use the property of quantum states, and in practice, it is the Heisenberg uncertainty principle, where like you don't know in which basis the information has been encoded, and you can only know if you happen to measure it with the same basis that has been encoded. Otherwise, you get random information.
Yeah, I guess very very quickly on that point, right? Like the idea behind the random basis is these will function as your parity check bits to make sure that there is no eavesdropper, if I'm getting that correctly, right?
So yeah, the technicality of the protocol is the following: is that some of the string we measured in the correct way, and we keep those bits. The ones that we didn't measure correctly, we put them on the side, and then we're trying to do some sampling to see if there was some eavesdropper. Because if there was some eavesdropper, they would have taken the message in between, but because you cannot clone that message, you cannot copy, because the moment you try to measure it, if Eve tries to measure the quantum state, then they would not know the basis themselves. And so when they send a new quantum state, which is like a fake quantum state, this with enough sampling can be spot. It's like there are in total 4 chances, and the probability is like 3 over 4 on the power of n.
Yeah, for the people out there, that's like, think of it as like you can send some stuff, which, like, depending on how you measure it, will be either information that you get, which you're encoding via some error correcting code, so you can always decode it, or B, you're going to get some checksum bits. And the checksum bits will, like, the statistics of the checksum bits will indicate whether there was an eavesdropper on the channel. Because by construction, by no cloning specifically, we have this weird property that, like, if Eve measures the thing on the channel, she will change the statistics of what the outputs are. right? So what Bob will see will be like a different, like statistically quite distinct. So this is the same thing as like we do in ZK proofs, right? In ZK proofs, we have this like thing where we have a bunch of like a huge message and we sample little bits of the message and we check that they're consistent with like some underlying set of operations that we expect. Right. And we do this via error correcting codes partially, and then we do this via these like weird proximity tests or whatever. We're doing exactly the same thing here, except like we're doing a similar statistical test here, except one is like over one basis, and then one is like over like the basis which actually gets you information. And one of them will tell you whether there was an eavesdropper, while the other one will tell you what the actual message should have been. So that's roughly like mapping it down.
I think for any listener who heard our episode with Yelena, we did actually talk about a similar case in that one.
Exactly.
You've talked now about a couple of these applications, but I feel like in your exploration of this intersection, are there other things that you've discovered are possible, even theoretically, at this point?
Yeah, for sure. I'm going to say some, and I'm sure Alex has a bigger list. There are some things that you can do beyond quantum key distribution. There's these private quantum money solutions that you could try to experiment with. And then more broadly, in theory, we know that we have new kind of, if you also had compute, you could enter like a new realm of applications. So for example, there are digital copy protection programs or, copy protection programs. Essentially, I can give you a program that you can run, but you cannot make copies of. And so you can give it to someone else, but you cannot make copies of. And in a more, say, extreme way, there is this idea of one-time programs. Unfortunately, you cannot have one-time programs without hardware assumptions. One-time programs are not possible neither in classical nor in quantum. But with some trusted hardware, you can have these one-time programs. And there are some groups that are working on these one-time programs. And the beauty of it is that you could encode, say, financial, for example, you could encode an option in a program that I send to you. And then you can decide whether or not to exercise the option without talking to a ledger or without talking to anyone. And this program only runs once. So this is a cool idea. Definitely could have a lot of impact. And then you have other applications. One that I find very interesting is quantum position verification.
Is this like a GPS?
Yes.
It's like a physically based GPS.
But what are you trying to, you're trying to say that something is somewhere? How would you do that?
So in practice, you play on latency because you cannot make information travel faster than light. That's the principle. The question
it's latency. It's how long it takes to get somewhere. Okay.
Yes. The issue with it is building this in a secure way. It's very hard. And then there is other problems that come to mind is a quantum random number generation.
Mm-hmm.
And in a more broad sense, there is this concept of device-independent cryptography that you could apply to all the things that I just mentioned before. You could have device-independent QKD, device-independent quantum number generators. Device independence means today, if you run a protocol, you need to trust the machines that you have that is correctly running the protocol. In a way, when we buy a ledger or like a hardware wallet, we don't know if it's running correctly.
Yeah.
The nice thing about device-independent cryptography is that you can test the ledger to see if it is correctly executing the protocol, which is pretty exciting because all of a sudden you don't have to trust the hardware.
I don't really get that though. Device independent. Like what makes it independent of the device? Like maybe I just don't fully understand what the connection that exists now is.
I'm not entirely sure, to be honest. This is one of the more extreme things. Actually, at the event that you came to, there was the inventor of device-independent cryptography that gave a talk.
Okay.
Roger Belko. My understanding is that you're able to basically query the device, and you're querying it in a specific way. You're trying to see if there's a Bell inequality violation that tells you you're trying to, without the technicality, which I'm not like super familiar with, you're trying to test whether this device is really a quantum device. And if it's not, then you know that it's been either tampered with or that it's faulty. If it is, given the output you give it, it's going to give you given the input you give it, it's going to give you a certain output that's going to tell you, oh, okay, this is legit. And so for that reason, it's device independent in a way, because it doesn't mean you don't use any devices, right?
Yeah.
It means you use a device, but it means you can ask the device before, like, hey, are you messing with me or not? And you know that whatever answer it gives you is a truthful answer.
Okay. I think when you said device independent, I thought it was more like some program can like exist on multiple types of device that are very different from one another. But that's not what
it
you
is
meant.
slightly confusing. Yeah. What it means is really
Okay.
like you're removing it. It's like trustless hardware in a way. So the way this person Roger explains it as well, he also says now you can have quantum hardware made in factories that you do not trust, and you're still able to check whether the hardware was tampered with or not.
Interesting.
Or you can have someone else run the hardware somewhere else, and you're able to check potentially remotely if you have like a quantum connection to that hardware, that the hardware is running correctly, with some probably things that I'm missing here.
Are you using is this the same as we described before, where like if someone has eavesdropped, it's different? Is
Yes.
that what this is playing on?
He's using the same idea. So the way to think about it is, imagine hardware that does two things. Number one is it spits out a ZK proof that like the output is correct. And number two, it also spits out a, roughly speaking, quantum proof that it has not copied any of the bits anywhere else into the machine.
Okay.
Because if you were to do that, you would be fucking with the statistics of the underlying thing. Like, this is not quite a perfect analogy, but that's like the best way to think about it. It's like, what is the problem of a machine right now? Like, the machine itself could be doing all sorts of nonsense and sending out data to like other things. There's no way for us to know that in a digital world.
Yes.
Right? Because again, you can copy data, you can send it out, you can keep it in a bunch of stuff, you can do additional processing on it, and you would never know unless you like knew how the machine worked. But we can prove that the output of the machine is like correct. Like the output that it hands you, Anna, right, like is good by just like giving you a ZK proof or a sync proof or whatever. But now, again, we now don't know this property of like we can't copy out things from the machine.
Yeah.
Right. And so the like big brain version of this is like, okay, sick. But like here's a cool thing that like guarantees that people haven't done copying of this underlying state.
Because if there had been any observer, you would get a different outcome. You couldn't make that proof.
So in some sense, like it like, again, it's not exactly sync proof, like there's like a fancier quantum thing that you can do with this. But fundamentally, the point is the same. It's like, you know, the computation is correct and you know that nothing else has been done, because if anything else would have been done, like it needed to like observe the data that is passing through these pipelines for it to like go out and like give you the right result.
Nice.
So there you go. That's maybe like the analogous, like weird conglomeration of the two things. I don't know if that scans Alex or Nicola.
No, yeah, I mean, I think that was great. What's exciting about it is, you know, if you think of the current movement in the blockchain industry of like trusted hardware, you could think that the end game of trusted hardware is you don't have to trust the hardware at all. If you know, that's a mean way of saying it, but I think that's it. So I think, you know, some of the people working
execution environments.
Trusted execution environments.
I just put trusted. I just added another trusted.
Those.
Like we add another ZK, but yeah.
You know, I think that could be very, very exciting. Obviously, there's a lot of limitations to this. There's like extra overhead involved in like a device independent protocol. Again, that's my understanding. But my understanding is you could make them better. You could improve those protocols if there was like demand for doing that. And so again, from the point of view of the crypto industry and the point of view of some of the problems that the trusted hardware people are facing right now, which is, well, these chips are fabricated by large corporations. We don't have access to them. Like they might
something
insert,
could be in
like,
there,
backdoors in it. Exactly. Exactly. And this is kind of saying, well, let them build the hardware, and we're just able to test it independently. You have similar things happening where you're able to test hardware with like infrared scanners. I don't know if you've heard of this. This is not quantum anymore, but this is still crypto physics to some extent, where you're able to scan the chip to understand if like anything has been tampered with. I don't know the details, but there are people working at that intersection as well. Sorry, this is like a side note to what Nico was saying, but there are scaffoldings towards quantum hardware that starts from more traditional hardware that just improves its trust guarantees over time, and that is quantum inspired. And there are people working on this. Sylvain, for example, if you've met him before, is one. He wrote this paper called "A Path Towards Crypto-Physically Secure Trusted Hardware," and with a lot
From
of
which project?
He was at IC3, and now he's building his own company around this, and kind of building this trusted hardware and improving the guarantees based on different physics assumptions you can make on it. So that's one exciting thing, device independence. I think Nico mentioned a lot of other primitives that are cool.
Yeah.
Some of them are based on unclonability. Some of them are based on entanglement as like the two key primitives. And then you can build cool stuff with each of those kind of things. One that I will shout out for Guillermo and that I don't know a lot about
Oh God.
is you can use entanglement for coordination and to play.
You have to play to correlated equilibria versus playing
Yes.
to standard mesh. Yeah.
And so there is this paper called Quantum Bidding in Bridge, where people say that if two players that are playing together in a bridge game, so this is not blockchain bridging. This is like the game of bridge.
Bridge, card game. Okay.
Yeah,
Yeah,
exactly,
that one.
exactly.
Grandparents' game.
If they share an entangled photon, they're able to win more frequently because they're able to coordinate better. So there's this kind of overlap with like kind of game theory or like some of like advantages in games and entanglement that's quite interesting. Some people have started to think about it in the context of financial markets for some specific use cases, which is mostly theoretical, but that's an interesting intersection that I don't think people have been thinking a lot about practically, but that is also exciting in the context of using entanglement as a primitive. And to go back to a previous application that Nico mentioned, the same way you have copy protection, you can also have certified deletion. So this is all playing with the same concept of unclonability, but in different ways. And for each of these sub kind of use cases, you know, if you have a little bit of imagination, you could potentially think of things you can do with that, right? If you can prove that you can certify that you've deleted something in a verifiable way, even if those two parties do not trust each other, it augments our communication kind of systems with new ways to communicate with one another. And so again, from a crypto mind's perspective, it's kind of like being kids in a candy store.
Yep.
So many things to play with.
In a way, we started with the North Star, which is it's not the only North Star, but it's like an exciting application, which is quantum money. Then we discussed like some applications that are more broad than quantum money, but only some of them, unfortunately, are practical today. So what I'm trying to say is I want to excite the listeners, but I also want to give caution, which is the only thing that we know is practical today, meaning you don't have to come up with new hardware. It's QKD, but there are a few others that could be implemented today. And one in particular that I care a lot about, and I'm trying to talk to everyone so that everyone knows that this is possible, is this paper from Orsatat and others, which, by the way, Or also has been in the show.
Yeah. That was a great episode
Is
series.
the tokens for MAC. And MAC is this primitive of in cryptography, which is a message authentication codes. The idea is I give you a code that then when you give back to me, I can verify that I gave you the code. And this is used in many places. But the issue with MAC is that I can only generate these authentication codes myself because I have the secret key to do it. Imagine for a second that I want someone else to generate an authentication code on my behalf. The naive solution would be give them the secret key. You understand that this is not good because then they can generate as many authentication codes as they want. And the beauty of this paper is that it introduces this idea of tokens that can be spent, quantum tokens or quantum state, that can be spent, and by spent I mean measured, in a specific way so that you can generate one MAC only on my behalf. So it would work more or less like this. I create some quantum states, some photons, I send them to you. If you had memory, you would keep them until you need them. But without memory, you would spend them straight away. And by spend them, it means you would measure the quantum state that I sent you to generate an authentication code. And you can only generate one authentication code only.
One application of this that we have in crypto is actually from my former project, Flashbots. One offshoot little toy project that they did is called teleport.best. And using trusted hardware, but not quantum stuff. But again, with trusted hardware, you have some phantom quantum properties. They were able to create this platform where, let's say this marketplace where I have a Twitter account and I'm able to sell access to my Twitter account and to a single tweet that other people can buy this token and they can spend it to write a single tweet from my Twitter account. And I don't have to reveal any information about my Twitter account to them. And they don't have to reveal who they are as well because you're using the properties of the trusted hardware and you're using some form of unclonability in that sense. So again, this goes back to the point I was making before where one path that you could see towards the crypto space becoming more quantum pilled is through trusted hardware to some extent, because trusted hardware offers you some quantum inspired properties. And so you could think of building applications that are kind like teleport.best, which is more of a toy application than anything else, but you're already building the user expectation around unclonability, and then you're able to just improve the guarantees behind it. That's one thing I'm excited about. Anyway, that's one toy application, right? But it's cool that it opens up this market. Now you can use it, and you don't have to fear. Well, assuming you trust the trusted hardware, you don't have to fear that someone is going to get your Twitter account, and you're able to sell fun access tokens to your Twitter for like one tweet, and you're able to do cool stuff with it. So you can imagine maybe that for more useful applications, but that's one way to apply this practically that kind of made sense and that went slightly viral and people started using it, at least for a short amount of time.
The beautiful aspect of these tokens for Mac is that you're creating this new concept of a physical resource that gives you access to something. It is almost like a capability. In distributed systems, the concept of capability is it's very fascinating, which is if you want to write into a file, you need to be, generally there is like a list of people that can write into the file. In capabilities-based systems, someone gives you the capability and you can give this capability to another process, but the process can write into the file as long as they have the capability. So this idea of capabilities, I think it's very synergetic with this idea of tokens for Mac. You could move around this token to whoever they need it, but they can only spend them themselves once. With this idea, I gave a presentation at the Quantum Punks event we organized in Paris on like directionally how you could be building quantum-based layer 2s. In a ways you can think of it as like an instance of private quantum money. And the idea is we could be building a bridge from layer 1 into a quantum network, where in this quantum network, I could move these tokens around. And whenever I'm done transacting, I can settle them back into the layer 1. It's a big complex, so I would probably send the listener to go watch that video. And unfortunately, there's not clear protocol yet, but I would love for new brains to go and trying to find what are the intersection between what's possible today and cryptocurrencies, because our whole thesis is that if we find an application like this, we could accelerate the space like we did for zero-knowledge proofs.
Wow. Are there any other like open problems or areas that you're brainstorming about or that you've noticed people are working on?
So there's a few. Number one, to keep it short as well, is whether we can allow people to remotely and classically connect to quantum networks. And so this would bypass the hardware constraint entirely, right? One of the criticisms that you guys might have for quantum cryptography is that, well, I need quantum hardware. This is going to be
super expensive, hard to get.
Expensive, and like it's just a friction, you know? It's like a hurdle that I have to overcome. And so I need to be motivated to do this. And that's friction that kind of drags people experimenting with it, et cetera. And so one thing we've been looking at is, could you at home classically connect, by classically I mean with your computer in classical communication, connect to a quantum network in a way that is trust minimized, or in a way that you would be able to fully verify whatever operation is done in the quantum network was done based on how you wanted it to be done, and in a way that's privacy preserving as well. So there are protocols that are called, for example, remote state preparation, they're very inefficient protocols, but that kind of start going in this direction of thinking about, okay, how can someone remotely prepare a state for me? And then remote state measurement would be the other side of this. And so you can do this in a trusted way today, right? It's just an API where you just need to talk to the quantum network and it needs to prepare the photon the way you want it. If you trust whoever is preparing the photon, that's easier. And so that's one thing that we're excited about, because if you manage to do this well, it can start trusted and then it can progressively improve its guarantees. We get into a new paradigm for quantum kind of networking and cryptography, where now Guillermo and you, Anna, can hack on quantum networks via your classical computer.
Cool.
And so that, I think, is like one
Wow.
hurdle that we see as potentially accelerating things, and that's very achievable. At least the trusted version of this delegation, trusted delegation, achievable in like 3 months. It's like just a matter of this software that's needed. That's my understanding. If you want to do verifiable, then you need actually cryptography work to improve the protocol. And that's a little bit more complicated, but I imagine that this would be something that a lot of cryptographers and quantum people would work on if there was kind of this demand for, okay, now if we had this particular thing that's verifiable, and if we can improve the overhead massively by some math tricks or some application-specific verifiability, I think they would start thinking about this more if there was this kind of use case. So that's one thing I think we're exciting about as a problem, because it is short term. It accelerates kind of the pace of the space. And it's a very concrete kind of developer experience problem in a way. And it also pulls on our, at least more Nico than my expertise, but like, verifiability and these things are like problems that Nico had to look at in the context of Filecoin, in proof of storage and these things. Like, how can someone prove that they have, storage somewhere else?
I was wondering if you had mentioned sort of there not being quantum memory. Is there anyone working on quantum memory?
Yeah, so there are people working on quantum memories, and actually at the event in Paris, there's one presentation on it. Maybe we can link it in the description of the podcast.
Yeah, are the videos out for that?
I just uploaded them. I need to add the titles.
Okay.
They're not like public. I need to put the titles on them, but
maybe by the time the episode airs, they will be though.
100%. Yeah.
Perfect. Okay, we'll add them in the show notes then.
Great.
Nice.
So people are building quantum memories, and they're building kind of different flavors of quantum memories, is my understanding. So there's different ways that you can trap this information. Some way is like purely photonic, where you kind of trap the photon and you're trying to keep it. And some ways is you convert the photon to another object, and then this object is more stable, and then you're able to keep it there. And then the challenge becomes now you have to reconvert the object back to a photon later. And so this conversion part are called transducers, right? Guillermo briefly mentioned transducers earlier on.
Yeah, we also chatted about it in the previous episode as well.
Nice.
Because this is Yelena's been working on for a while.
So, I mean, it's super exciting. This is a technology that is needed for quantum computers.
Yeah.
And so people are working on quantum memories to help synchronize multiple quantum processing units that are connected together. So if you think distributed quantum computing, you need to synchronize those units together. And to synchronize them, you need for a short amount of time to kind of like hold their state together. And so this is where the memory comes in. And so the unfortunate thing is that a lot of quantum memory companies that we talk to, which by a lot, I mean like 5 of them, but it's big in that space, that were distributed all over the world. What they told us is they started as a quantum networking companies, improving the capabilities of quantum networks. And what they found out is, well, there isn't a ton of demand for kind of better quantum memories. However, in quantum computing land, there is demand for it. And we have these clients, which are quantum computing companies that are willing to pay for it. And so some of them have slightly steered away from the pure networking applications towards it's still a networking application, but it's to connect quantum processing units in data centers next to each other, So people are working on this, and some of the results that they have are super encouraging as well. But so that's another problem that's hard and like difficult to deal with. And
it's funny. I mean, it feels a lot like memory, just like in classical sense, right? Like our memories used to be like literally magnets with like wires that cross over, and you could only hold them for a long enough time. Then afterwards, there were these acoustic bits, actually, where you would encode bits as like a traveling sound wave that would reflect a few times, and you'd have to like measure it on the out. I don't know if you guys know about this, like
I did not know that. That's amazing.
So it's like, it's funny. It's like the same thing, but we used to have this for bits in the digital world too, right? We couldn't just holding bits is like a weird thing. Like, yeah, you could kind of read them and write them down in a way that you can't with quantum state. But it's like very similar, like doing anything more than, a few things, like turns out to have been really hard up until like shockingly recently.
No, I think part of this journey, what has been interesting is kind of looking back at our stack, the normal internet stack, and realizing how complex it is and how much improvement it has undergone over time. and how much it's like super technically complex as well. And so that has been fascinating and very interesting, and also encouraging to think that, well, this took time, kind of what you just mentioned, Guillermo. To close on quantum memories, why it's exciting, why it's a high leverage kind of technology to develop is because you need them for repeaters. So if you have better quantum memories, basically the longer the quantum memory is, up to some number of time and the number of photons, etc. Let's make it simple. The longer the quantum memory is, the bigger the network can be, basically. What's interesting is there's kind of there's like 1 microsecond, 1 millisecond, 1 second, maybe 1 minute. And then at the 1 minute mark, you get to like the covering the whole world. And then from 1 minute onwards, my understanding is you don't have a ton more things. And so to get like persistent memory, this is what I don't understand. But for quantum money, my understanding is you need some form of persistent memory or something that can carry over. And so that's an interesting thing. But it's a high leverage issue for that reason, where you can enable multiple things if you have better quantum memories. So that's number 2 in terms of like cool problems that I think we're looking at and we're interested in. The quantum memory one is more of a like research interest. The first one is more like, hey, if someone builds this, you can enable commercial activity and at least like hackers to start building. But yeah, maybe to give just a very quick like mental model, there's one that's about how can we enable people to build on quantum networks faster.
Yeah.
And there's another kind of camp that is how do we improve those networks in terms of their capabilities, their memories, the distance of the network, the compute capability, which is related to transducers as well. And so those are kind of the 2 broad areas. And the first one is more interesting in terms of if you can catalyze activity in that first one, we think it's going to impact that second one.
Nice. Amazing. Alex, Nicola, thank you so much for coming on the show and covering that intersection between quantum and cryptography, sharing with us so many of the applications that are already being considered, those of the future. This has been super interesting. Thank you so much.
Thank you guys. Super fun.
Thanks for having us.
Hopefully soon, quantum crypto podcast, QC podcast.
Maybe Crypto Punks podcast?
Yeah, I like, if I have one contribution to like the meme is, I would say, how about computational cryptography and physical cryptography are the 2 distinctions. There you go.
Oh,
I like that.
cool. Well, thanks again, guys. I want to say thank you to the podcast team, Rachel, Henrik, and Tanya, and to our listeners. Thanks for listening.